Hello and good afternoon friends, welcome to the CEC EduSet live lecture. Dear friends, as you know that we have conducted 3 lectures on thermochemistry. Today also we are going to talk on thermochemistry. We are going to get a deep knowledge on this very topic. Dear friends, for this we have again with us in our studios Dr. Amit Kumar. Dr. Amit Kumar is Senior Assistant Professor in Department of Chemistry, the Al Singh College, University of Delhi. So dear friends, let's welcome our guest Dr. Amit Kumar and let's try to understand more on thermochemistry. Hello sir, welcome to the EduSet lecture.
Thank you very
much. So far we have conducted 3 lectures and this is the 4th lecture. I hope that we would be conducting the last lecture on thermochemistry, or we have more.
I do believe that this should be the last lecture.
Definitely. So dear friends, let's move forward and let's have a knowledge on thermochemistry more and more. So over to you sir.
Thank you very much. First of all, I wish very good afternoon to all the viewers. Dear friends, today we are going to have 4th lecture on thermochemistry. Let's have a little recap of what we have done. We have defined the enthalpy of reaction using the molar enthalpy data of products and reactants for a particular reaction. We have also observed that molar enthalpies values, absolute values, we cannot determine. So enthalpy of formation, which we had made use of, where enthalpy of formation data is not available, we are making use of other enthalpies such as enthalpy of combustion, etc. But Hess law is the one which helps us to calculate the enthalpy change of many reactions, and we have seen this, that Hess law has been very important, which allows us to manipulate the chemical reactions and treat them as algebraic equations, and we can manipulate them by adding, subtracting, multiplying by certain numbers, and correspondingly we can also manipulate their enthalpy changes to get the enthalpy change of our desired reaction. If suppose for some reactions that is also not possible, now what is to be done? And in this lecture we are going to start with that very aspect. Although we had touched this aspect in our previous lecture, but also we would like to add certain more information about this aspect. This aspect relates to the bond enthalpies for the dissociation of various bonds. So now let us see what way we do define the bond enthalpies of a given bond. The bond enthalpy is the average of enthalpies required to dissociate a particular bond present in different gaseous compounds into free atoms or radicals in the gaseous state. So we would like to see what it does actually mean. But before we do that, let us have a look at what is bond dissociation enthalpy. The bond dissociation enthalpy is the enthalpy change associated with the dissociation of a specified bond of some specified compound. So therefore, it does mean that, suppose for example we have water. In water we have 2 equivalent OH bonds, and whenever first of the two OH bonds undergoes cleavage, we need to provide heat in order to dissociate this OH bond, and correspondingly we have dissociation, bond dissociation enthalpy of the first step, as because we have dissociated the OH bond in water molecule, and that represent delta RH standard, its enthalpy change is 501.87 kilojoule per mole. Now we have a different chemical species now. The remaining chemical species is the hydroxyl free radical. It also has OH bond, but the hydrogen atom is bonded to oxygen atom only. It does not have any other atom bounded to it. So therefore now when we break this OH bond in hydroxyl radical, there will be different enthalpy which will be involved in this reaction, that is 423.38 kilojoule per mole. So what I mean to say is that bond dissociation enthalpy refers to the enthalpy change associated with the dissociation of a specified bond of some specified compound. However, on the other hand, the bond enthalpy is the average of enthalpies required to dissociate the said bond present in different gaseous compounds into free atoms or radicals in the gaseous state. So therefore, for example, if we want to determine bond enthalpy of OH bond, then all we need to do is we need to take the mean of the average of the bond dissociation enthalpies of OH bond once in water molecule, the other time in hydroxyl radical, and when we take the average, what we end up is end up with is nothing but the bond enthalpy. So, bond enthalpy is the average value of the bond dissociation enthalpies for a particular bond for a number of molecules in which the pair of such atoms appear. We can illustrate with the example of decomposition of methane as well. In methane molecule, there are 4 CH equivalent CH bonds. However, whenever the first CH bond undergoes cleavage and it leads to formation of methyl free radical, and thereafter it leads to the next dissociation of CH bond occurs, then it leads to formation of active methylene compound, that is CH2 carbene, and thereafter it is CH dot, and then ultimately the carbon atom and 4 hydrogen atoms gets produced. So, all we mean to say is all these 4 CH bonds will be cleaved from different starting species. First CH bond will be cleaved from methane molecule, the second CH bond will be cleaved from methyl radical, the third one from CH2 double dot, and the third one at the fourth one will that is the fourth CH bond will undergo cleavage from CH triple dot. So, therefore, there will be different bond dissociation enthalpies for CH bond, but if we do take the mean of all the bond dissociation enthalpies, then it will become the bond enthalpy. For example, over here we have the decomposition reaction of methane. It leads to formation of 1 carbon atom and 4 hydrogen atoms in the gaseous state, and this also has the enthalpy. This reaction would then have a enthalpy change that will be designated by symbol delta H. Then, since this reaction has led to cleavage of 4 CH bonds, then we can divide this delta H by 4 in order to get the bond enthalpy of CH bond. In this manner, we can get the bond enthalpy of CH bond. The bond enthalpy of CH bond can other way around can also be obtained using Hess law. Let us have a look at this reaction again. That is the decomposition reaction of methane, which leads to formation of 1 carbon atom and 4 hydrogen atoms in the gaseous state. This reaction can be split into 5 different reactions as a sum of these 5 reactions. The first one is the combustion reaction of methane. In presence of 2 mole of oxygen, 1 mole of methane undergo combustion to form 1 mole of carbon dioxide and 2 mole of water in liquid state. The second one is nothing but is the reverse reaction of the enthalpy of the formation reaction of carbon dioxide. Third one is twice the reverse reaction of formation of water. Fourth one is represent the twice the decomposition of hydrogen single bond, and the fifth one represent the transition of 1 mole of graphite in carbon in the graphite state to carbon atoms in the gaseous state. So, when we take the sum of all these reactions, it leads to ultimately this final reaction. Correspondingly, we can also add the enthalpy change for these different reactions, these 5 different reactions, and the addition as a result what we get is delta RH standard, that is the enthalpy change for this decomposition reaction. So, what I mean to say is we can also make use of Hess law in order to get the enthalpy change for this decomposition reaction. And now, if we want to determine the bond enthalpy of CH bond from this data, then all we need to do is we need to divide the enthalpy of decomposition of methane by 4, since there were 4 CH bonds, and then what we get is just nothing but the bond enthalpy of CH bond. Now, it is important to note that the value of CH bond enthalpy does not correspond to the CH bond enthalpy which we have determined in this manner does not correspond to dissociation enthalpy of the first CH bond in methane. That is, whenever first of the 4 CH bond undergoes cleavage, it requires 427.77 kilojoule per mole of thermal energy. However, we have determined bond enthalpy as 415.85 kilojoule per mole. So, therefore, bond dissociation enthalpy, it is very clear from this data, varies from bond enthalpy. In nutshell, we can say bond enthalpy is just the average of bond dissociation enthalpy of the same bond in different compounds. So, therefore, having said this, we now switch over our attention to what is the importance actually of determination of bond enthalpies data, bond enthalpy data. Basically, the bond enthalpies are useful properties, that is useful in a way that these allows us to make estimates of approximate values of enthalpy change in reactions, where we cannot determine the enthalpy change of such reactions using experimental data, or by manipulation of Hess law also. That means such experimental data is not available to us, using which we cannot determine the enthalpy change of a reaction. In the absence of such data, we can make use of bond enthalpy data to determine or to calculate the enthalpy change of such reactions. However, it should be noted that enthalpy change calculated using bond enthalpy data should be used only if more accurate data is not available. Why it is so? It is so because the values which we are making use of bond enthalpy, that may not be exactly corresponding to the bond dissociation enthalpy of that particular bond in the desired compound. As a result, we can say as a conclusion in bond enthalpy, use of bond enthalpy data, that it should be regarded with great caution. It just allows us only to make certain approximate estimation only. Let us have a look. For example, if we want to determine the enthalpy of formation of selenium chloride from the bond enthalpy data. Now, here the reactants in this reaction is selenium, along with it there is chlorine. So, when selenium and chlorine combines, they do form selenium chloride, and both these selenium and chlorine, they are present in their most stable state of aggregation, that is selenium and solid state as a hexagonal crystal structure, and chlorine is present in the gaseous state. So, therefore, what we need to do is we need to first of all decompose this whole crystal lattice in order to have selenium in the gaseous state. 2 mole of selenium in the gaseous state. Whatever the enthalpy it requires is termed as delta RH2, and 2 is being applied over here because 2 moles is required. And since 1 mole of chlorine is also is required, which decomposition of which leads to formation of 2 atoms of chlorine in the gaseous state for every chlorine molecule, and it also requires delta RH1. So, thereafter, when these atoms have been formed in the gaseous state, when they do condense to form bonds in selenium chloride, which involve the formation of 1 single selenium bond and 2 single selenium chlorine bonds. So, it means we can make use of bond enthalpy data here, that is whenever these bonds are formed, heat is evolved, and therefore, we have for this enthalpy change we have used a negative sign for the bond enthalpy of selenium bond and twice that of the enthalpy of bond enthalpy of selenium chloride bond. So, therefore, in this way, when we add all these quantities, these are with negative signs, and tabulate the data, we can get the enthalpy of formation. Similarly, we can also determine the enthalpy of reaction. For example, if we want to calculate the enthalpy of reaction for addition of HCl to ethylene in order to obtain ethyl chloride. So, here in this reaction we have 2 reactant species. When we look at the stoichiometry, each has 1 as the stoichiometric coefficient, and here when the ethylene undergo decomposition, it requires heat corresponding to dissociation of 1 carbon-carbon single bond and 4 carbon-hydrogen 1 carbon-carbon double bond and 4 hydrogen and 4 carbon-hydrogen single bonds. So, we have seen you can very easily see that I have written the enthalpy involved in this decomposition is 4 times the bond enthalpy of CH bond, and along with this is bond enthalpy of 1 carbon-carbon double bond. And in order to decompose the HCl, in order to make hydrogen and chlorine atoms in gaseous state, we also need to provide heat corresponding to bond enthalpy of HCl bond. And when we provide this much heat corresponding to these two decompositions, it results to the formation of gaseous atoms. For example, it leads to formation of 2 carbon atoms, 4 hydrogen atoms, which are resulting from decomposition of ethylene. And when HCl undergo decompose, for every 1 molecule of HCl which undergo decomposition, it leads to formation of 1 hydrogen atom and 1 chlorine atom. All these atoms do align themselves in the structure which leads to the formation of ethyl chloride. Here you can see easily that all these atoms align themselves. Here I have shown with the dotted lines, it means the gaseous atoms are present. They align themselves and ultimately they do form, upon condensation they do form the ethyl chloride. And in the formation of ethyl chloride from these atoms, it requires formation of 1 carbon-carbon single bond, 5 carbon hydrogen single bond and 1 carbon chlorine single bond. And therefore, heat will be evolved corresponding to the bond enthalpy of 5 carbon hydrogen single bond, 1 carbon carbon single bond and 1 carbon chlorine single bond. So, therefore, all of them are given with negative sign. And when we sum the enthalpies for all these steps, that represent the enthalpy change for the overall reaction. So, we can say that the enthalpy of the specified reaction can be calculated as enthalpy change of a reaction, that is equal to enthalpy required to break reactants into gaseous atoms, added to which is the enthalpy released to form products from gaseous atoms. So, therefore, here you can see, as we have shown in the diagram itself, 4 carbon hydrogen single bonds have been decomposed, 1 carbon carbon double bond has been decomposed and 1 carbon and 1 HCl bond has been decomposed for 1 molecule of these two reactant species. And finally, these gaseous atoms have aligned themselves in order to form the product ethyl chloride, in which 5 carbon hydrogen single bonds have been formed and 1 carbon carbon single bond has been formed and 1 carbon chlorine single bond has been formed. And adding these bond enthalpy data, finally tabulating their values, we get the enthalpy of reaction for this desired reaction. So, I want to make a caution over here. We should make use of bond enthalpy data in order to determine the enthalpy change of a reaction when and only when we do not have other methods for calculation of enthalpy of a reaction. Since this method only provides us an approximate estimate to the enthalpy change of a reaction. So, in summary, we can say enthalpy change of a reaction can also be determined as sum of bond enthalpies of reactants minus sum of bond enthalpies of products. Now, you can easily see that why students sometimes have confusion in a way that enthalpy change of a reaction is represented as sum of molar enthalpy of products minus the sum of molar enthalpy of reactants. Sum of molar enthalpies of sum of enthalpies of formation of products minus sum of enthalpies of formation of reactants. But over here, when we take the bond enthalpy data, the enthalpy of a reaction is determined as sum of bond enthalpies of all the bonds in reactants minus sum of bond enthalpies of all the bonds in the products. And this you can easily see with the help of diagram which we had shown earlier, that since cleavage of bonds is required to be done in reactants, so this should be given negative sign, negative of a negative quantity become positive. So, therefore, it leads to a reversal kind of a formula, that is enthalpy change of a reaction is equal to sum of bond enthalpies of reactants less the sum of bond enthalpies of products, each having multiplied with their respective stoichiometric coefficients. Having said this, we now also have a look at the resonance stabilization of benzene from the viewpoint of the enthalpy of formation calculated using the bond enthalpy data. Suppose, for example, we want to decompose benzene in order to get 6 carbon atoms and 6 hydrogen atoms. If we carry out the calculation for this reaction using the bond enthalpy data, what we will get is we will be required to give 5368.5 kilojoule of heat we need to supply for every 1 mole of benzene, which when undergoes decomposition to form 6 mole of carbon atoms and 6 moles of hydrogen atom as well. However, the experimental value when it was determined, it was found to be 5535 kilojoule per mole, and in this manner, using the bond enthalpy data, that is, we require to dissociate 3 carbon-carbon single bonds, 3 carbon-carbon double bonds and 6 carbon-hydrogen single bond. Tabulating the data, we get the enthalpy change of this reaction using the bond enthalpy data. However, from experimental value, it amounts to be higher. What it does mean? The bond enthalpy data tells us that we require only 5368.5 kilojoule per mole of heat in order to bring about this reaction. Experimental value tells us that it is required, the experimental setup requires 166.6 kilojoule per mole of heat, more than that of that which has been calculated by bond enthalpy data. It is clearly an indication that benzene structure, which involve 3 alternate single and three single and double carbon-carbon bonds, it is not present as such, but the electron density involving the double bonds which has been made by pi bonding, they are present, they are actually not localized, the electron density is not localized over very different carbon atoms, but the electron density is delocalized over the whole benzene ring, and it leads to stabilization of benzene ring, and this stabilization is actually known as resonance stabilization. In organic chemistry, we talk much about very many different kind of reasoning is being given using the resonance stabilization of molecules, and this resonance stabilization is accounted for only by using the thermochemical data, using the bond enthalpy data and the experimental decomposition data. Having said this, now let us give some attention to determination of enthalpy change at some different conditions, different from the one in which enthalpy change have been experimentally observed. For example, if we have certain reaction for which we have determined and we have calculated the enthalpy change of a reaction, and then if suppose our objective is to carry out this reaction at some different temperature, suppose for example at elevated temperature, then we again will have to calculate the enthalpy change of that reaction in the same manner as we have done it earlier. But there is a remedy also, we can make use of Kirchhoff relation in order to obtain the enthalpy change of the desired reaction at different temperatures. For this, let us have a look how we can do it and what actually the Kirchhoff's law means to us. Kirchhoff's law is useful actually for determination of enthalpy of a reaction at a temperature different from that at which value is available. Now, in order to, if we want to derive Kirchhoff's relation, let us consider a general reaction. Suppose there are several chemical species which are present in the reactant side, say for example capital A, capital B, these are chemical species which do participate in chemical reaction as reactants and so on, each having stoichiometric coefficient which is being given by their small letters. For example, chemical species A has small letter A stoichiometric coefficient, chemical species B has small letter B as stoichiometric coefficient, and it leads to formation of several products such as capital L, capital M. These represent the products chemical species and having their stoichiometric coefficient represented by small letters small l and small m. Now, having said this, for such a reaction, if we want to determine enthalpy change of a reaction, simply we can just say it is the sum of molar enthalpy of products less the sum of molar enthalpy of reactants, each multiplied with their respective stoichiometric coefficient. So, in this equation 2, now can we differentiate this equation? Idea is, can we differentiate this equation with respect to temperature keeping the pressure constant? Answer is yes, we can. Let us see if we do so, what we will actually get. We had delta RH at the left hand side and various molar enthalpy terms at the right hand side. So, therefore, let us consider their differentiation with respect to temperature at constant pressure. So, we can write del of delta RH by delta T at constant P, which is equal to small l times del of molar enthalpy of species L by delta T at constant P. Similarly, small m times del change in molar enthalpy of species M by delta T at constant P, that is change in molar enthalpy of species M with change in temperature at constant pressure, and so on. We can take the sum from which, from this sum of products we can subtract the sum of similar sum for reactant chemical species A del HMA by del T at constant P plus B del HMB by del T at constant P, and so on. Now, having said this, let us recall back what is molar heat capacity. It is just nothing but the rate of change of molar enthalpy with temperature at constant pressure, that is Cpm equal to del H by del T at constant P. Cannot we recognize all these del H m L by del T, del H m by del T as the molar heat capacities? Yes, we can. So, since this holds true, so our equation 3 transforms to equation 4, in which small l times Cpm, that is molar heat capacity of species L, plus molar heat m times small m times molar heat capacity of species M, and so on. We take the sum of all these heat capacity terms of the products, from which we subtract the sum of molar heat capacity terms of all the reactant species, and ultimately what we get is the delta RCP, that is the difference of heat capacities of products and that of the reactants. That is what we get is delta RH by delta T at constant P equal to delta RCP. This is delta RCP is thus just nothing but the sum of molar heat capacities of products less the sum of molar heat capacities of reactants, each multiplied with their respective stoichiometric coefficient. We can rearrange this equation to get equation 5, just have a look. D delta RH, when we take dt to right hand side, what we get, d delta RH at constant P equal to delta RCP dt. Now, we can integrate equation 5 at constant pressure within a temperature range from T1 to T2. What we will get is integral T1 T2 d delta RH equal to integral T1 to T2 delta RCP dt. If delta RCP, that is the difference of molar heat capacities of products and reactants, or in other words the molar heat capacities are assumed to be independent of temperature between the temperature range T1 to T2, then we can say we can take delta RCP outside of the integral and we can integrate the equation. What we will get is the enthalpy change of the reaction at temperature T2 minus enthalpy change of the reaction at temperature T1, that is equal to delta RCP into T2 minus T1, or in other words we can say delta RH, that is enthalpy change of a reaction at temperature T2 minus enthalpy change of reaction at temperature T1, that is equal to delta RCP into delta T. And therefore, just by tabulation of the data, for example, in the T2 temperature, the temperature which is the desired temperature at which delta RH T2 enthalpy of reaction we want to determine. If we have the enthalpy of reaction at temperature T1, the value of temperature T1, the value of temperature T2, and as well as we have the difference of molar heat capacities of products and reactants, then all we can, or in other words the molar heat capacities of all the species which do participate in the chemical reaction, then we can determine the enthalpy change of the reaction at temperature T2, that is the other higher temperature, desired temperature at which we want to determine enthalpy change of the reaction. So, it does mean with the help of Kirchhoff's relation we can, if we have enthalpy change of reaction at one temperature, we can calculate the enthalpy change of the same reaction at some different temperature. But here we have made one assumption. The assumption is that delta RCP, molar heat capacities of all the chemical species which do participate in the chemical reaction, they are independent of the temperature range between temperature T1 to T2. So, this is the one assumption which we have made. Now, having said this, now let us consider if these molar heat capacities does not remain constant over the temperature range for within which we want to calculate enthalpy change of reaction. So, therefore, we need to also make these molar heat capacities a function of temperature. Let us have a look how then this Kirchhoff law will transform. In that case, we can say that molar heat capacity of each of the chemical species can be represented as a power series in terms of temperature. with several constants such as A dash, B dash, C dash. These are constant characteristics of the substances which do participate in the chemical reaction. Having said this, so we have delta R Cp, which is just nothing but stoichiometric coefficient times the molar heat capacities of products. It's their sum, from which we need to subtract stoichiometric coefficient times the molar heat capacities of all the reactants. So here in each term, molar heat capacity of species L, molar heat capacity of species M, molar heat capacity of species A, and molar heat capacity of species B. For each of these molar heat capacities, we can substitute the molar heat capacities in terms of equation 8, that is the coefficient A dash, B dash, C dash, which will be different for different chemical species. So ultimately, when we substitute equation 8 in equation 9, then what we will get is if we substitute equation 8 in this equation, then what we will get is equation 9, that is delta R Cp equal to delta R A dash plus delta R B dash into T plus delta R C dash into T square. So how we will read the right hand side? Right hand side is just nothing but the difference of these coefficients which are constant characteristics of chemical species such as A dash, B dash and C dash of different products and reactant chemical species, and ultimately what we get is delta R A dash, delta R B dash, delta R C dash, which would then be constant, which would then does not vary with temperature but would be independent of temperature. So delta R CPM, if it varies with temperature, so we have transformed the equation and we have specified the delta R Cp as CPM as a function of temperature using the difference between constant characteristics of chemical species. Now having said this, so therefore let us now again consider equation 6, where integral T1 to T2 d delta RH equal to T integral T1 to T2 delta R Cp dt. So if we substitute for delta R Cp in terms of equation number 9 here, then what we will get is, we will get the integral which will be having several terms such as delta R A dash plus delta R B dash T plus delta R C dash T square by 2 and so on and so forth. So ultimately when we integrate it, what we will get is delta RH T2 minus delta RH T1, which is equal to, when we integrate all these terms individually, then it means it will be equal to delta R A dash T within the temperature range T1 T2, delta R B dash T square by 2 within temperature range T1 T2 again, and delta R C dash T cube by 3 temperature range T1 T2 again. So thus if we know the enthalpy of reaction at temperature T1, that is delta RH T1 if we know, and we know that T1 and T2, and knowing the constants A dash, B dash and C dash for all the reactants and products chemical species, we can determine the enthalpy of reaction at temperature T2. So this is what the Kirchhoff's law is very promising and helps us to determine the enthalpy changes of several reactions for which we need not repeat the experiments at different temperatures. All we need to do is we can make use of Kirchhoff relation and we can calculate the enthalpy change of reaction at different temperatures. But it is important to note that if suppose for example, if a reaction goes on in a manner such that if you have carried out a reaction at temperature T1, and if you want to determine enthalpy change of the same reaction at temperature T2, such that when you consider the enthalpy change at temperature T2, some of the chemical species which do take part in the chemical reaction, their phase transition occurs. Suppose for example at temperature T1 one of the chemical species is present in the liquid state, and at temperature T2 it is present in the gaseous state, then you will be required to add to the calculated enthalpy change of the reaction at different temperature or higher temperature using Kirchhoff law. To this you will be required to add the enthalpy change for the transition of that chemical species at lower temperature to that of higher temperature in a different phase. Let us have a look at it with the help of an illustration. Let us consider the decomposition of methane. Let us consider the combustion of methane, at 298 Kelvin. in the combustion reaction of methane, 1 mole of methane combines with 2 mole of oxygen in the gaseous state, and they do form carbon dioxide in the gaseous state again at 298 Kelvin, and also leads to formation of 2 mole of water in liquid state. But now if you want to determine the enthalpy change of the same reaction at 500 Kelvin, you must make a note of the fact that at 298 Kelvin, which is just nothing but 25 degrees Celsius, water is present in liquid state. However, at 500 Kelvin, that is greater than 373 Kelvin, which is the boiling point of water, the water will be present only in the gaseous state. So, the delta RH which you will determine at 500 Kelvin using the Kirchhoff relation, you will add to this value the enthalpy change for transformation of water, 2 mole of water in liquid state at 298 Kelvin to 2 mole of water in gaseous state at 500 Kelvin. For example, it means you will have to add the value of delta H standard for this reaction, that is 2 mole of water in liquid state at 298 Kelvin undergo transformation to 2 mole of water in gaseous state at 500 Kelvin. You will have to add this delta H naught value to delta RH T2 value in order to actually get the enthalpy change for the same reaction, that is combustion of methane at 500 Kelvin. So, how you can determine the enthalpy change for this reaction, for example, for this transformation of water in liquid state at 298 Kelvin to 2 mole of water in gaseous state at 500 Kelvin. We can split this reaction in terms of three different reactions, thermochemical reactions, where in the first 2 mole of liquid water is heated from 298 Kelvin up to its boiling point, that is 373 Kelvin. Here we can make use of heat capacities or heat capacity of water, and we can estimate, we can determine the enthalpy change for the first reaction. Let us consider the second reaction, where 2 mole of water in liquid state at 373 Kelvin undergo phase transition from liquid phase to gaseous state. Then we need to also add the enthalpy change for this reaction. The third reaction is the heating process, is basically the physical process, that is heating process, that is when we heat 2 mole of water in gaseous state at 373 Kelvin and bring it to and take it to 500 Kelvin. So, corresponding to these three processes, if we add the enthalpy change, then what we will get is the enthalpy change for transformation of water in liquid state at 298 Kelvin in liquid state to water in gaseous state at 500 Kelvin, and this value we need to add to delta RH T2 value using the Kirchhoff relation we had determined. Then actually it will get us the enthalpy change for combustion of methane at 500 Kelvin. Having said this, now let us consider how we determine the enthalpy of combustion. For this we need a bomb calorimeter, which is just nothing but a vessel which is evacuated and is closed, where at in the vessel we have in very small pot we have our reactant chemical species, and a spark plug is provided, and a spark is produced, because of which the combustion occurs in presence of oxygen, a desired amount of oxygen outside there, and the heat is released. The heat which is released by this combustion process is absorbed by the calorimeter as well as the water which is enclosing this calorimeter, which ultimately is finally sealed with the help of an adiabatic valve. So, whatever the heat gets produced due to combustion reaction in this bomb calorimeter is being absorbed by this bomb calorimeter along with the water which is in which the calorimeter is immersed. So, therefore, the heat released in combustion reaction is equal to heat absorbed by water and bomb calorimeter. Thus, Qcom, that is heat evolved in combustion process, equal to negative. Here it is evolved, so it is positive sign. Here it is absorbed by water, so that is equal to negative. Here, because Q water and Q bomb, these are positive quantities, so they are negative quantities because this is absorbed. So, negative multiplies become. So, therefore, heat absorbed is a positive quantity and heat evolved is a negative quantity. So, heat appears due to combustion reaction. So, during combustion heat evolves, that is being absorbed by a water and calorimeter. When they absorb, they have a positive value of the enthalpy. Just a minute. Yes. So, heat that is evolved in the combustion process, that is equal to heat absorbed by water and Q bomb. So, a negative sign is been applied because here it is evolved and here it is absorbed. So, absorbed is these are positive quantities and which is multiplied by negative quantity, then it gives the negative quantity to Q com, that is combustion process the heat evolved. So, the heat absorbed by water and bomb calorimeter are determined through their specific heat capacities. That means, if we have Q water and Q bomb, then we can determine Q comb. So, this heat absorbed by water and bomb calorimeter, that we can determine using their specific heat capacity. Just have a look at how we do determine it. If amount of heat required to raise the temperature of mass m of a substance by temperature delta T is Q, then amount of heat required to raise the temperature of mass m of a substance by 1 degree will be Q by delta T. Similarly, amount of heat required to raise the temperature of 1 gram of a substance by 1 degree will now be equal to Q by delta T, that will be again multiplied, that will be again divided by m, that is Q by m into delta T. M is the mass of substance, delta T is the temperature change, and Q is the heat required to raise the temperature of substance by 1 degree. Total change in temperature. So, specific heat capacity of a substance is designated by symbol small c, whereas capital C is being used for heat capacity. So, specific heat capacity is just nothing which is equal to the heat required to raise the temperature of 1 gram of substance by 1 degree Celsius. On the other hand, heat capacity is the heat required to raise the temperature of some substance, a fixed quantity, by 1 degree. So, it is very clear then heat capacity will be a multiplication of mass and as well as the specific heat capacity. So, these relations do hold true. So, Q comb equal to minus Q water plus Q bomb, and therefore, m water small c, the specific heat capacity of water, plus m bomb small c, and m bomb and small c bomb, which become equal to heat capacity of calorimeter, and therefore, thus knowing mass of water, the heat specific heat capacity of water, the heat capacity of calorimeter, and the total change in temperature being produced in the system, the amount of heat evolved in the combustion reaction can be determined. Once we determine the heat evolved in the combustion reaction in this manner, all we need to do is we need to divide it by number of moles of the substance which undergo combustion. Then what it will give us, since the system was a closed system, so the heat evolved will be equal to the change in internal energy. So, that will be equal to internal energy of combustion. So, that is determined in this manner. So, the enthalpy change, that is the enthalpy of combustion of the substance, then can be obtained as is equal to the change in internal energy of combustion process plus delta nu g RT, where delta nu g is just nothing but the difference of sum of stoichiometric coefficient of products and sum of stoichiometric coefficients of reactants. So, in this manner we can determine the enthalpy of combustion of a substance. Now, let us consider the physics. These were all the characteristics of a chemical reaction. Now, let us consider the one of the physical process, that is the solution process. Let us have a look what occurs in the dissolution process. Suppose, for example, if we have some sodium chloride, and if we add this sodium chloride in distilled water, what happens? It spontaneously undergo dissolution and a solution is formed. But actually, how a solution is formed, with the help of this illustration, just have a look. If in the solid phase we have the sodium ions and chloride ions at the fixed lattice sites, and basically in the solution what occurs is that all these ions, how the dissolution occurs is, all these ions first of all surrounded by the water molecules which are dipolar in nature, which they establish the ion dipole interaction. When the extent of such ion dipole interaction net force is greater than that of the interaction which these ions experience by oppositely charged ions in the lattice, then the ions which will be termed as solvated ions and will be set free in the solution, and this is how the dissolution process occurs. The same dissolution process we can split it in two forms. One is lattice energy, that is one process in which the ions in the lattice do undergo decomposition and leads to formation of gaseous atoms, and then gaseous atoms then undergo solvation, that is hydration here in this case, because water is our solution solvent. So, therefore, the enthalpy of hydration is involved in the second step, and ultimately the solution is formed. And when we take the enthalpy changes for these two steps using the Hess law, then we determine the enthalpy of solution. Now, see, so it means whenever we dissolve a substance, there occurs an enthalpy change. You must have noticed when you dissolve glucose in water, it leads to that the temperature of the glass is lowered. You will sense that the glass gets cold a little bit. What it does mean, the temperature has decreased. It means the dissolution process is an endothermic process in that sense. Suppose for example, if you dissolve potassium nitrate in water, then you will observe the glass gets warmed. What it does mean, the temperature gets increased, and that occurs because of evolution of heat. Basically, as we have seen, solution process is a sum of two processes, one is lattice energy and one is hydration energy. When hydration energy is exothermic in nature, and lattice energy, because in order to break the lattice, in order to form gaseous atoms, you need to supply heat. So, this is an endothermic process. If the weightage of lattice energy is higher, the dissolution process will be endothermic in nature. If the weightage of hydration energy is higher, the dissolution process will be exothermic in nature. So, in that sense, you can say this accounts for the fact some solution process for some of the substances is exothermic in nature, whereas for others it is endothermic in nature. And we just wish to here define the integral enthalpy of solution. Integral enthalpy of solution is just nothing but is the enthalpy change when 1 mole of solute is dissolved in a definite quantity of solvent to produce a solution of desired concentration. While recording integral enthalpies, it is recommended to state the concentration of the prepared solution. Maybe in next lecture, some of the remaining portions regarding this enthalpy of solution we would try to cover. Thank you very much.
Definitely, we would be covering the remaining part in the future sessions, that is in forthcoming sessions. And till then, friends, take care, goodbye, and keep watching these lectures with the help of the YouTube. Thank you, sir. Thank you so very much.